on mathematical transition for fermions with Igor Poboiko from Karlsruhe. Please, I will make up.
Okay. First of all, I'd like to thank the organizers for inviting me here and giving me an opportunity to present my work, which was done with my collaborators from Karlsruhe Institute of Technology, Paul Peperl, Igor Gorny, and Alexander Mirdin. And the story will be related to the previous talk by Adam. Namely, it will be also about the monitor dynamics of free fermions, but in this case, this will be complex fermions with the standard time-independent Hamiltonian evolution. Okay, so this is the outline of my talk. First of all, I'll also try to, in somehow repeating what Adam was saying, but from somewhat different perspective, I'll try to give a general introduction about the story of measurement-induced phase transitions, and namely the story about the monitored free fermionic case, which has some peculiarities as you could have gotten from the previous talk. Then I'll explain the field theory that we managed to develop to describe this system, namely it's related to the Keldysh nonlinear sigma model with peculiar replica limit R to 1. Yeah, then I'll present some numerical results for the model, and if time permits, I'll also give a few words about what we expect to happen when you include interaction. Okay, so yeah, the story begins as follows. Let's take just the usual free fermion system. Now it's described by time-independent Hamiltonian, just the usual hopping Hamiltonian. Let's say on a d-dimensional cubic lattice. I'll talk about role of dimensionality a bit later. In this case, you can think of 1D chain or any other chain actually. Yeah, so this one ingredient, you prepare a state, arbitrary state, it may be an eigenstate of this Hamiltonian, it doesn't really matter. And then you let it evolve. But apart from the standard Hamiltonian evolution, you also include randomness in a sense of random local measurements of some operators. In our case, it will be density, but again, I'll try to be as generic as possible. So my measurements, meaning that at some point I have my Krauss operators, I'll be working in Krauss operator formalism. Then corresponding to some observable, I do a measurement, I can get one of the outcomes alpha, described as corresponding Krauss observables. Probability of the given outcome is given by some generalization of Born's rule, which is the average of this k dagger k, the standard formula and the Krauss formalism. And again, if you do a post selection on the measurement outcome alpha, then you get the von Neumann wave function collapse, namely your wave function changed in a jump manner after the measurements by multiplying by this operator k and then renormalizing of the wave function back to unity. So these are two crucial ingredients of my evolution, namely unitary evolution and these random local measurements. Let's see how it looks like on the practice. This is some cartoons for the one-dimensional spin chain of size 200 with periodic boundary conditions. X-axis corresponds to the position, coordinate in the chain, y-axis corresponds to time, and different pictures correspond to different measurement rate per time. So per unit time, I have gamma measurements. And this is gamma smaller, 0.1, and this is gamma equal 10. And you see different things happen as you increase gamma. Let's start from the rightmost or leftmost picture, this one. Here you see that on average, the density, the color marks the density of your state as a function of time. And you see that on average, the picture is almost white, which means that density is around 1/2. It was half filling case. And then you see the bright blue or red spots corresponding to density equals 0 or 1. These spots are precisely correspond to the measurements that projected this given site at either 0 or 1. It's either empty or occupied after you learn the outcome of this measurement, which means that you produce some local fluctuation of your density. And then this fluctuation spreads over your system due to unitary evolution. And on a larger scale, you see that, it's on average around, on average, you have rare weak fluctuations around 1/2, which we will describe by means of some long wavelength field theory. Okay, as you increase the measurement rate gamma, dramatic things happen, namely when gamma is 10, the situation is completely different. Namely, your density, the contrast of the picture is very different. You almost everywhere you have either blue or white. which means that each side is either empty or occupied, and the state itself is almost a product state. And this is the quantum Zeno limit, where you measure so frequently that your wave function collapses into an eigenstate of all your observables that you measure. They commute, so such eigenstate exists. In our case, it's more or less a bit stream, and no unitary evolution happens. This is why this has this emergent vertical line pattern. Time evolution almost doesn't happen. It still happens because gamma is not infinite, but in the limit gamma to infinity, you have this quantum Zeno limit. And this leads me to this story of measurement-induced phase transitions, namely, there is a way to actually qualitatively and quantitatively characterize this kind of difference of the behavior by means of the entanglement entropy. Essentially, we'll argue that two states that we have to the left and to the right have a different behavior of the entanglement entropy. These are probably all familiar formulas for most of you. Namely, you take some subsystem of your system, you trace out the rest of the system, you get reduced density matrix, and then you calculate Renyi entropy or the usual entanglement entropy. Importantly, for U1 case, for the case where the particle number is conserved, you can actually introduce something that is somewhat easier to study, and actually you can use it interchangeably with the entanglement entropy as another probe for your measurement-induced phase transition. Namely, it's the quantum fluctuations of charge in the same subsystem. And the reason for this, so yeah, these are cumulants. You can also study the cumulant generating function, which is generating function of cumulants. Yeah, and yeah, the reason why you can use these two probes interchangeably is, for example, the Cauchy-Schlitter relation, which holds for any Gaussian state. And same as the previous talk, it will be actually very important that the protocol that I described preserves Gaussianity of the states. This is, I think, the most important thing that leads to this nonlinear sigma model description. But nevertheless, yeah, for Gaussian states, these are actually related. So if you know the charge fluctuations, then you can also get the entanglement entropy. Furthermore, it's actually a series and infinite series, but in our case of interest, the series just is dominated by the first term. So again, we will use the entanglement entropy and the fluctuations of charge for the most of my talk interchangeably. Okay, so this sets me at the ground to, there is a story about this observability of the measurement-induced phase transition in the real-life experiment, and this is a story about you cannot see the title, but it's actually about post-selection problem. Yeah, the thing is that, what I was talking about is either quantum fluctuation in a given quantum state, given quantum pure state, and I only get a pure state in the end of my evolution if I do a full post-selection over whole of my trajectory. Which means that in order to study, let's say, fluctuations of charge, I need to reproduce the same trajectory multiple times. That's the only thing, that's the only way on the experiment, how can I gather the statistics, right? And there are actually exponentially many of such trajectories, namely 2 to the m, where m is the number of my measurements. Which means that in order to reproduce the same trajectory, and each trajectory is random, in order to reproduce the same trajectory, I need to rerun my experiment, if I had like a real realization of my system, exponentially many times. And this is the post-selection problem, which actually makes this thing hard to observe in a real experiment, in real hardware. But nevertheless, it's kind of useful from many different other perspectives. Namely, it's related to the computability of your system on a classical computer of your experiment. Namely, if you have highly entangled state, it's hard to simulate on a classical computer. But if you have a weakly entangled state, then it's somewhat easier. So it's nevertheless, I mean, this question is quite relevant for physics. Okay. And the thing is, yeah, now the story about the measurement-induced phase transition. So I have described what we are looking at in this random protocol. Namely, we're looking at the entanglement entropy or charge fluctuation in the subsystem. And there are several possibilities of its scaling with the subsystem size. The usual, the one that everybody would expect in a generic kind of case, is where your entanglement entropy follows the volume law, where it's proportional to the volume of your subsystem. This is again something that you would expect if you just take the random typical many-body Hilbert space state. Typically, it has volume law entanglement. On the opposite corner of my phase diagram, let's say, is the area law, where you have like a state which is like a product state or almost a product state, or a state with a finite correlation length, where your correlations decay exponentially, which is the case for gapped ground states of some Hamiltonians, then yeah, you would expect the area low because you have only local entanglement between pair of sides near the boundary of my subsystem. And in principle, you can also have something in between, like critical behavior. One of the famous examples is the ground state of free fermions, or any other conformal field theory. In 2D, it also has this kind of logarithmic scaling of your entanglement. And the measurement in space transition, let me formulate it formally, is the transition between different scaling in the thermodynamic limit of your entanglement entropy, let's say, when you change the control parameter, which is in our case the rate of my measurements. So the question we would like to ask is whether there is transition between different scalings, and what is the transition, what are the phases, and what is the universality classes, and so on and so on. Okay. Now, some history very quickly. Actually, it's more or less well established by means of mapping on some classical stochastic problems, or by numerics that people did in different systems, is that in a generic, in a sense, random unitary systems, unitary circuits, for example, or interacting many-body systems, there exists a transition between a phase from a volume law with a volume law entanglement to the area law entanglement. Okay, area law entanglement is something that you would naturally expect with a large measurement rate, where you have the zero limit, which is typically is an area law entangled phase. And again, the volume law, as I said, this is something that you would naturally expect in a generic situation. Okay, the free fermions actually turned out to be very much different from a generic system. This is not a generic system at all, and the volume law phase is not realized that anywhere. And instead, the question that was in literature is whether there is a stable phase which has this logarithmic scaling of the entanglement entropy, or the logarithmic scaling is just an intermediate phase, and what you have is the area law phase. This is not complete list of relevant references, but yeah, this is the question that I will focus in my talk, whether the logarithmic phase is actually stable in the free fermions or not. And yeah, I would say that most of the work in this context was done numerically, and with numerics, it's always complicated. It's always hard to interpret data that you have with finite size scaling and so on and so forth. And there are actually objective reasons why it becomes even harder, which I'll explain later on. And spoiler alert, yeah, we will support this part of this fight. Namely, we will argue that there is no phase transition for one-dimensional free fermions, and there is just a single area law phase. And the logarithm that people see is actually just an intermediate asymptotic. Okay, so now how much time do I have? Yeah, 15 minutes. Okay, now I'll quickly go through the analytical approach to develop, which is based on the replica limit and so on and so forth, replica freak that Adam has already introduced. But yeah, I'll more or less repeat what he said, but with a different formalism, which is essentially the same. Okay, so the key object in our approach is this non-normalized density matrix, which can be easily obtained by taking your initial density matrix and then multiplying by a set of Krauss operators corresponding to a given outcomes. So, which we were taking at a different time. This thing, it's defined for a given trajectory, and what I call quantum trajectory means that I have fixed all the observables that I measured, all the outcomes at times at which they are measured. So I fixed all the random parts of my protocol, and if I fix them, yeah, then I get a well-defined matrix, non-normalized density matrix. Well, the usual density matrix can be obtained by normalization of this non-normalized density matrix. But the thing is that this normalization factor has a very crucial and very important property. It actually exactly coincides with the Born's rule probability of a given quantum trajectory. And this is the most crucial part from which this replica limit R to 1 arises from. Namely, if you want to average any observable which can be rewritten in terms of the n copies of your original density matrix, for example, you can take the second range entropy, which is trace rho squared, and n is equal to 2. You just take this formula, and what you get denominator, you get rid of denominator using the usual replica trick. But the thing is that what you obtain in the end, you obtain R copies of your non-normalized density matrix D, and you trace out R minus n of them to get this prefactor, and this prefactor is trace of D to the power of 1 minus n, which means that you have to take the limit R to 1. So essentially, again, I emphasize that this limit R to 1 comes precisely from this extra trace of D prefactor, which comes from the Born's rule. So this will be inherent for any measurement-related problem where you have this. You have to sum over your trajectories with the Born rule probabilities. Okay, so this is the first crucial ingredient, and the thing is, the main reason why we're looking at this matrix D, because its evolution is actually linear, unlike the evolution of the whole density matrix, which are based on linear equations of motion. And linear evolution is something that we typically like, something that we can describe analytically. Okay, so when you do this linear evolution for your matrix D, then you apply the standard theory. For example, you can do the Keldysh path integral trick, and in the Keldysh formalism, you obtain a field theory which is formulated for each individual replica, for each quantum trajectory. You get a theory which is quadratic in your fermions, and essentially it's described by this non-Hermitian Hamiltonian H plus Im, where H is a constant Hamiltonian by Hoppian Hamiltonian that I had in the very beginning, and M describes measurements. And I only can write this field theory in this way. It's quadratic only if my measurement operators are quadratic. So this will be the important thing. In the case that we were studying is the monitoring of density corresponds to this universality class. So the take-home message from this field theory is actually the following. You see that the effective operator that enters this quadratic Hamiltonian, first of all, is 2 by 2. Secondly, it's manifestly chiral. So it anti-commutes with tau z, it has this purely off-diagonal structure, and it's random due to this M of t, which has random measurement outcomes and measurement times. So we're dealing with a random, and furthermore, what is more important actually, that this operator is not Hermitian. So you double the system, you introduce this plus and minus Keldysh space, and in this setup, you have a Hermitian system, which is chiral manifestly due to this Keldysh structure, and it's random. So then you can actually map it. This is the mapping that we said, and these kind of random chiral systems can be conveniently described by terms of nonlinear sigma models, just like an Anderson insulator. Okay, except the only difference is this unusual, non-trivial replica limit that we have in this problem. Okay. So yeah, now let me quickly describe how the theory looks like and what are its implications. The theory is formulated in terms of this replicated fermionic fields. It's described in terms of 2R by 2R matrix, which lives in the Keldysh and replica space, and it has this block structure. If you take just the blue part, this Q with indices, it's a 2 by 2 matrix. It describes the replica symmetric sector, which describes these hydrodynamic modes that Adam was talking about. So on average, so first of all, yeah, this is a replica symmetric sector, which means that it describes the behavior of average density matrix. It describes the Lindbladian dynamics, which is known to be trivial in the systems in the sense that on average, you do not see any measurement-induced phase transitions. You do have to induce this post-selection in order to probe this transition. Okay, and this behavior of your average density matrix is described by this replica symmetric sector. It's 2 by 2 matrix, which is equivalent actually due to constraints by just a 2-dimensional sphere. So you can think of it as a let's say unit vector on a 2-dimensional sphere. And physically, yeah, it describes the non-post-selected quantities which depend on the average density matrix. For example, with the help of it, you can extract this type of correlation function, where you have just a single average of a single density matrix. Okay, and then on the off-diagonal sector, same as Adam had, we can put also the U matrix, which is R by R special unitary matrix for our case. And the reason for that, again, you can see just from the perspective of symmetry is that you have a chiral system, you have a chiral disordered system without any extra symmetries. If there is no extra symmetries, then it's a chiral unitary class. And chiral unitary class is A3. It precisely corresponds from this sigma model classifications, precisely correspond to the special unitary group matrices. Okay, and this non-trivial sector, this determines the behavior of non-trivial stuff that is related to this entanglement and so on and so forth. Okay, so quickly, the replica symmetric sector turns out to be quite easy. It actually describes just a simple diffusion. It doesn't have any corrections, quantum corrections whatsoever, as the diffusion constant is not renormalized, and it can be actually exactly, all the coupling constants can be exactly mapped to the corresponding microscopic values. So it's more or less simple. Not much to see here because it's described just the intensity matrix. And more interesting stuff happens when you take the replicon sector, this replica symmetric sector, which describes by this special unitary matrix. More or less, the thing that you can do is this. Okay, you have this field theory. It lives in a semi-space because, okay, you measured up, okay, thank you. You measured up to some time t, then you stop, and then you ask the question, okay, what are the entanglement properties of the states that I obtained, or what are the charge fluctuations, which means that I take my field theory, I describe it in a semi-infinite space in time. The time runs from here to there. So this is the time where I stopped my evolution. This is the initial time, which I take to minus infinity. And at time tf, I can ask different physical questions. In our case, again, we are interested in two types of questions. One is related to the information, the entanglement entropy, the purity, and so on. And another is related to the fluctuations of charge. And actually, both quantities can be very conveniently mapped, calculated with the help of this nonlinear sigma model by introducing a special form of boundary conditions on this side. Again, this is very similar to what Adam had with. So yeah, in order to calculate these observables, you have to just calculate this path integral with your nonlinear sigma model with some specific form of boundary conditions. Okay, then the results. The first important result is the first thing you can do. You can take the limit g to infinity, which is a prefactor of this, which is semi-classical approximation, which means that you have just to solve the classical equations of motion. This is much easier than to study the quantum problem. And what you get in this limit is you get parallel decay for the density correlation function, which means that both the charge and the entropy, this parallel decay corresponds to this area law with logarithmic convection scaling. So in 1D it would be just a logarithm because area in 1D is just a constant. Okay, so this is the first important prediction. Yeah, I didn't tell you that the control parameter that we have in our case is a rarity of measurements. So if measurements are sufficiently rare, if your measurement rate gamma is very small compared to J, the bandwidth of your Hamiltonian, then this result will hold. And then if you include quantum corrections, which are controlled by this parameter, if you include loop correction to this nonlinear sigma model, you see that actually this coupling constant G renormalizes and decreases upon scale increase, and you want this quantity G to be large for your semi-classical approximation to work. And what it actually tells you, this one loop RG result, is that the system flows towards a strong coupling. And again, these types of field theories, they naturally arise when people were studying the Anderson transition. And this flow towards the strong coupling that we have here is looks very much like the standard Anderson localization in two-dimensional system, except that here it's in 1D because the mapping goes from d-dimensional system to d+1 dimensional random system because you have to include time. Okay, so the prediction then is the same as in the two-dimensional standard Anderson transition, namely you always have localization for 2D. But the localization length is exponentially large, which means that before this localization length, you will indeed see this logarithm, but after that, in the thermodynamic limit, they'll actually always saturate at the area law transition. And this, we believe, is the reason why this controversy in the literature appeared in the very beginning, because you never can reach exponentially large scales in numerics. This is just hard. you have to do your finite size scaling very carefully. We believe that we did it actually very carefully, and we were able to observe this kind of weak localization correction. I will not go into too much details, except that, okay, for technical reasons, we studied the problem with nearest neighbor hopping, which actually had an additional symmetry. So it does not correspond to A3 universality class, but it actually corresponds to chiral orthogonal class, which is the BD1. But this is not a big deal because in BD1 the result differs by just a factor of 2. This was pointed in the recent preprint by Adam and his colleagues, to whom I say thanks. This kind of corrected our first preprint. Okay. Then, if you go to higher dimensions, this was predictions for 1D system. If you go to higher dimensions, then again, 2D monitored system will expect it to look like 3D Anderson system. And in 3D, you can actually have an Anderson transition. And this is, you can do from the theory side, you can do epsilon expansion, 2 plus epsilon, which is in our case 1 plus epsilon, which kind of predicts the transition indeed. Or you can do numerics. The only thing is that you should actually look for a proper scaling variable, which will represent this G, the collapse of data for which will allow you to expand the transition. And it turns out that the very good observables that you can actually look at to get a crossing point which corresponds to transition is actually more or less identical to the mutual information between two regions. So we were looking at precisely that. We got this kind of picture. We see a very nice crossing point. The standard collapse analysis allowed us to estimate the position of the transition which exists in 2D systems and the associated critical exponents. So again, the main result is that in 2D, unlike 1D, you actually do have a transition between metal and insulator, except that metal has this critical scaling and insulator has this area low scaling. Okay, I'll then just skip the part with interactions, just a couple words. We see that if you include interaction, actually this continuous symmetry indeed breaks down to the discrete replica permutation symmetry times U1. You can actually also see it from the perspective of nonlinear sigma model. We can just derive the actual term which does the symmetry breaking if the interaction is sufficiently small. And then the symmetry breaking, actually, from that you can predict that actually there is, first of all, the relation between entropy and charge fluctuation breaks down. For the charge, you still have this logarithmic scaling. For the entropy, you see the stabilization of a volume low phase. Then you see that this breakdown of continuous symmetry also kills your localization, and it says the mechanism how the transition for charge happens, which is more or less identical to the charge happened in traditional, which was suggested by Romain Vasseur and his colleagues. It's more or less BKT transition for 1D systems. Okay, so the predictions for interaction system is that there can actually be two separate transitions for information and charge, unlike the case of the Gaussian systems. Okay, and yeah, this is more or less preliminary, so yeah, let me kind of skip that. This is the outlook of my talk. There are many directions to which we would like to push this nonlinear sigma model description. Now that you have established this mapping to corresponding Anderson problems, you can also now start playing with other models that will give rise to any interest in universality classes. You can try to implement something like quantum Hall effect, which means quantum Hall effect counterpart in this measurements setting, and so on and so forth. Yeah, with that, I'd like to thank you. Here is the summary of my talk, and I'm looking forward to your questions. Thanks.
So, questions? Oh, sorry. Yeah.
So about the symmetry classes, can you realize all of the Anderson localization symmetry classes are only a subset?
That's a good question. I mean, the symmetry, I mean, from this perspective, in order to get the symmetry, you have to look, you have to look at the symmetry of the corresponding quadratic problem, right? You have to look at the symmetry of this operator L, more or less, right? You see that it's chiral by construction, that naively you would expect that you can actually realize only chiral symmetry classes. But in fact, as you know, that if you manage to somehow add another chiral symmetry, then two chiral symmetries is actually no chiral symmetry. It means that you have a standard unitary symmetry. and with the help of which you can actually try to go beyond this restriction imposed by chirality. So we now think, at least we hope, that we'll be able to explore the whole set. Well, maybe not just us, but the rest of the community as well. We'll be able to explore the whole set of different universality classes. But we already know a lot of examples that you have suggested in your talk. You have D, D3. Here we have A3, D1, and so on. So it's already a pretty large subset. So yeah, I think I would expect that all of them should be able to be realizable.
Just one question comparing with the talk by Adam. So
yeah,
the fact that the beta function has different sign here, same,
yeah.
right? So do you have a way to understand at least a posteriori why the U1 makes this sign change?
Well, one important thing I think from physical perspective is that in Adam's case he measured even and odd links, and those are not commuting observables, right? Which means that the Zeno limit, if you measure super frequently, is not well defined. In our case, you can actually realize an eigenstate of all the observables that you measure. So you have this well-defined Zeno limit where your wave function collapses in the product state, and then you just leave it like that. And product state has an area long. But in Adam's case, he had non-commuting observables, which means that even if you measure them super frequently, you can still kind of expect the scale, the area low phase to survive only in some subset of phase diagram. Namely, for example, in Adam's talk, if the dimerization is 0, if you remember, if you measure even not with the same strength, you never realize area low phase whatsoever. You always have this log squared scaling, if I remember correctly. Right?
So your point is that you could have a log phase with U1 if you were doing a different kind of measurement, like something which is
okay.
desired.
So if you have U1, you either have BD1 or a 3 symmetry class. Okay, this actually, we think that there might be a possibility to actually stabilize the log phase as a phase. And one of the things is that actually A3 universality class supports for West-Zumina term. Here, we didn't have any West-Zumina, we didn't have any topology. You can actually try to derive it. I mean, we just don't see it here. But if the West-Zumina term is there, it will actually stabilize the logarithmic phase. But I'm not sure if it will lead to transition. You might always have the. So I mean, again, from the symmetry perspective, you can play the whole story. You can open this huge reviews with the tables of universality classes and see what you would get in a different replica limit, right? You can see, and then yeah, you can either have transitions or not. That's a very interesting.
Very good. Thank you very much. I think it's time to move to the next topic. Thank you again.